Okay, class, exponential equations. At this point, we have looked at the three R's. I want to review them right now. Talked about this before, and there's three main R's we want to think about with exponential expressions. The first one is actually two roots or radicals, kind of equivalent. The second one is reciprocals. And the third one is repeated multiplication. So we talked about that right from the start, that when we have an exponent on a base, that's a power, that's n factors of a. Okay, so we know that. That's the basic definition of exponentiation as an operation, is a repeated multiplication. Reciprocals involve something when we have a negative exponent. This would be repeated multiplication, but with the reciprocal of the power. And then roots and radicals occur anytime we have a fractional or rational exponent, where this is the nth root of a. And then we have something a little bit more detailed, where we have the nth root of a repeatedly multiplied m times. Okay, so we have roots, radicals, we have reciprocals, we have repeated multiplication. Now we can apply all those exponent laws when we're looking at examples that require us to solve an equation. And in this case, we'll come back to this example. We're going to develop a few methods that we can use to solve exponential equations. So this section is all about using the exponent laws when we're looking to solve for value of x in an equation that makes the left side equal to the right side. The investigate that we'll do in class is going to look at two strategies that are valid, and we'll look at why a third strategy is not valid. Let's start out by considering, how do we solve an equation like this? Well, we'll go through each one and we'll learn a little bit about solving exponential equations as we go. So the first one is really just something that needs to be said off the bat. When we have an equation where we have something like a power 5 to the x equals 5 to the 6. Both of these are powers, and the thing we want to point out is they have a common base. Okay, common base is something that is really a useful strategy, because as soon as the base is common, then automatically, since we have left side equal right side, that also means that we have a common exponent. Okay, left side equals right side means the powers are equal. And as soon as we have the bases equal, then that means we have a common exponent. In other words, in this case, x equals 6. Okay, so that's a strategy we're going to work towards in most cases when we can produce a common base. Now this is possible many times, sometimes it's not. Let's have a look at b, 2 to the x equals 32. By inspection, you can probably look at that and say that, you know, x equals 5 makes that true, because 2 to the 5 is 32 as a check. Okay, there's no need to really make a common base there, but if we were, we could write the left side as 2 to the x. We could write the right side as 2 to the 5th, and now we can clearly see that, again, with the common base and the powers being equal, we have to have a common exponent. Okay, let's move on and look at C. 7 to the exponent 3x subtract 4 equals 49. Now some of us are going to want to solve that by inspection. You know that 7 squared is 49, so you might be thinking, okay, I'll work with that, and that means that 3x subtract 4, which is the exponent on the power on the left side, is going to be equal to 2. So what would make 3x subtract 4 equal to 2? We'll solve that equation. We get 3x equals 2 plus 4, which is 6. So x equals 6 over 3, which is equal to 2. And as a check, we can go and check that value of x equals 2. The left side, it would be 7 to the 3 times 2 subtract 4. And that's 6 subtract 4, which is 2, which is 49. And so left side equals right side. So therefore it works, okay? The application of the common base there works as well, because the right side is a power of 7, and so as soon as we go to expressing both sides with a common base, we can then look at the exponents. 2, 3x subtract 4, they must be equal. Once we have a common base, then we can move towards using that information here. All right, let's look at what we've discovered so far. In this, let's drop down a little screen shade and show you the important parts here. The connect ideas. First of all, an exponential equation is one that contains a variable in the exponent. It's not just one that has an exponent in the equation, but where the variable is the exponent. So in contrast, x squared equals 49, that is not an exponential equation, because in that case, we don't need to use this strategy of common base. Our variable is the base. So here, we would just use the square root. Square root of x squared equals square root of 49. So that would give us x equals 7. That's not an exponential equation. It has to have variable in the exponent. So some examples are given. When we don't have technology, we can solve an exponential equation by writing both sides of the equation as powers of the same base, and this allows us to use the following property. It's given kind of a fancy name, equality of powers with a common base. What that means is when two powers are equal and the bases are common, then we can be certain that the exponents are also equal. Okay, and this applies whenever the base is not equal to 1 and more than 0. And let me just show why that would not work. If we had, let's say, an exponent of 1, we have 1 to the 3, and then that's equal to 1 to the 5. Well, we cannot say 3 equals 5. In that case, both powers produce the value of 1, but solving in that case would not give a meaningful result. So the equality of powers with a common base is the main strategy that we're going to use when both sides can be written with that common base. So if we look at the remaining questions here, we have increasing complexity here. We have 3 to the 5x plus 8 equals 27x. So let's tackle that one. So 3 to the 5x plus 8 equals 27. Okay, to the x. Okay, so we actually have an exponent on both sides. So here, I know things like, I know that 27 is 3 cubed, so I can write that off to the side. That's a fact that I can make use of. So what I would do is express both sides with base 3. So what I'm going to do is replace 27 with 3 cubes, 3 to the third. So this is common base. Okay, once that's done, then I can just apply exponent laws. So on the left side, there's nothing to do here, just carrying this through. But on the right side, we have power of a power. So we're going to multiply our exponents. 3 times x is 3x. Now we have equality of powers with a common base. Because the powers are equal, shown here, and because the bases are equal, here, then that means that the exponents must be equal. That's the only way for those two powers to be equal. So in this case, we can then say 5x plus 8 equals 3x, sort of a therefore statement, and then isolate x, subtract 3x from both sides. I guess I would have to add 8 there. It gives us 0. And then I will subtract 8 from both sides. And then I'm going to end up with 2x equals negative 8, so x equals negative 4. Negative 8 over 2, which is negative 4. And then at this point, I would just want to check that. Negative 4, okay, that seems possible. The right side with a negative exponent involves a reciprocal and repeated multiplication, but Here, the left side is a fairly complicated power, and it's hard to see what the exponent needs to be there to make them equal. But if I check by substituting a -4 for the left side and the right side, then what I can do is just verify that my answer is correct. So left side would be 3 to the 5 times -4 plus 8. So -20 plus 8 is -12, and that'd be 1 over 3 to the 12. And the right side is giving me something like 27 to the -4, which is 1 over 27 to the +4. And here what I'm really looking to verify is 27 times 27 times 27 times 27 the same as 3 multiplied 12 times over? Well, I mean, I've got 3 3s every time I write a 27, and when I have 4 of them, I'll obviously have 3 and 6 and 9 and 12 3s. Okay, so I'm going to have 12 3s multiplied, and here I'm also going to have 12 3s. Okay, so that would tell me that they're equal. I don't really need to use a calculator to verify what those numbers are. I can check it just by understanding repeated multiplication. All right, so the last example here, quality of powers of the common base. This is our strategy here that we're using. This would be the most complicated question that you might want to know how to do, is where you have a variable on both sides, and both sides have multiple terms in the exponent. So let's take this one here and just image it so I don't have to recopy it again. And we'll look at part E. So 2 to the 2x subtract 5. Notice the brackets there. Okay, so what we want to start with is common base, of course, will always be the smallest base. Or, in this case, one of the bases is the common base, which would be 2. So, and we know that 4 is 2 squared. So that means that we can replace 4 with 2 squared. And we got to be careful that whenever we do that replacement, that we don't do something like, that and just kind of, I'll multiply the 2 by the 3x. Okay, so we're putting in the 2 squared in the place of 4. Okay, which now means that really I should probably put my 3x subtract 1 exponent in brackets so that I keep it as the exponent on a power. And then on the left side, I will simplify what I can. 2x is 2x, and 2 negative 5 is negative 10. On the right side, I have power of a power I multiply. And so I would double 3x and double negative 1. So I would end up with 2 to the exponent 6x subtract 2. 2 to the 2x subtract 10. So question is, when is 2x subtract 10 equal to 6x subtract 2? Okay, so I now have common base, common power, they're equal, common exponent. So from that point, I can therefore 2x subtract 10 equals 6x subtract 2. I'm going to collect all my x's on the right side this time and my numbers on the left, and I'll do this all at once. So I'm going to subtract 2x from both sides, and I'm going to add 2 to both sides. Okay, and that produces 0 here. And now it produces like terms, which can be simplified, -8. And then my next strategy, of course, is to divide, so I can get a factor of 1. -8 over 4 equals 4x over 4, which is x, so -2 equals x. So that's what I think the value of x is. And again, I would always go back and check my answer here, and the check will be the last step, just to make sure. Separate the left side and the right side. Okay, whenever you do a check, you're really asking the question, is -2 equal to x? Okay, and until we know the left side is equal to right side, we can't write an equal sign between them. Okay, up to this point we knew the powers were equal, but let's say we make a mistake over here and I end up with, I goof and I get like, -4 because I accidentally subtracted them. Now I'm going to go check that and I find, okay, I'm going to put in 2 to the 2 times -4 subtract 10. And I can go to the simplified version of the left side, or I can go right back to the beginning. Okay, and I get 2 to the -8 subtract 10 is 2 to the -18. And the right side I'm working at 2 to the 6 times -4 subtract 2, and I'm getting 2 to the -26. Well, I mean, at that point I'd stop because I realized that -18 is not equal to -26. So I've done something wrong. Okay, but we know x is not equal to -4. So that wasn't what I was checking. What I was checking is it equal to -2? So 2 to the double -2 subtract 10 is -14. And on the right side we have 2 to the 6 times -2 subtract 2. And that gives -12 subtract 2 is -14. So I don't need to go any further. That I know that 2 to the -14 is the common power on both sides, so I'd stop and say, therefore, x equals -2 is the solution. Okay, and that is the strategy of equality of powers, where we're trying to produce a common base. Okay, now let's look at another example of solving an exponential equation with technology. This one here in your package is example 2. This is using systematic trial. We'll see then investigate. There's going to be systematic trial involved in solving that because the equation can't be solved using a common base. So when we have an equation such as 3 to the x equals 7, really simple equation here, but we would struggle to find, a power of 3 that produces 7. So we want to solve for the value of x to 2 decimal places, and in this case we're going to need a scientific calculator to work this out. So here's generally how the solution works in this case. We recognize, first of all, no common base is possible. That's probably the first thing you should be writing in your solution, is no common base, okay? And what we really mean there is no common base that's an integer. Okay, so that prevents us from using equality of powers with a common base. The first thing we need to do is break into where approximately x is by bracketing the two closest integers. So we know that, again, 7, somewhere between 3 and 9. Now 3 and 9, because 3 is the first power of 3 and 9 is the second power of 3. We know it's closer to 9. Obviously 7 is closer to 9, so we can expect our answer, x equals, to be closer to 2 than to 1. And again, notice here we have values that we're testing in the exponent, which of course are x. So again, x would be closer to 2 than it is to 1. Next thing we can do is try an initial value. So let's try something closer to 2 than 1. We try 1.6. Now that's just a first step, so there's nothing really wrong to do here in this first step. Don't choose something more than 2 or less than 1, and you should be really above 1.5. So you find that 5.8, not obviously 7, so it's too small. So you bring it up to maybe 1.7, you get 6.47. So it's still too small. So let's say you jump 2 units here in your next step, or you go 1 unit, and you're too large. We would really have been too large if we had tried 1.9. So 1.8 is close to 7, but obviously the value of x needs to be a little bit less than 1.8. So now we use, say, 1.78. Okay, so you notice we're only dropping down 2 100ths of a unit. So we're still above 7, still too large. So we have to make our exponent even smaller than 1.78, and we get to 1.77. Well, we're getting 6.99. Well, so that really, if we were to use 3 to the exponent 1.77, and 6.990. So it doesn't exactly round directly to 7 in the third decimal place, but it definitely does in the second decimal place. So I would stop there and say, well, 1.77 is probably a close enough approximation. Okay, and then we can use that as our systematic trial for solving this exponential equation. Okay, let's have a look at generally the strategy here then. when we have technology involved here. Scientific calculator, graphing calculator could be involved. The first method here with technology, when we cannot use a common base, is to determine between which two integers the solution lies, determine to which integer it is closest, and then narrow the search by using more precision, which is what we did there. Let's go back to the third example here, which sort of completes this lesson, and this would be using a graph. Okay, now we've used a little bit of graphing this semester. We've done graphing calculator work. Here we're solving 3 to the x equals 7 to 2 decimal places, but this time with a graph instead of systematic trial. So what I'll do here is I'll open up the graphing calculator on the screen. I'll show you the steps I would carry out to solve this question. All right, so systematic trial, not really something I want to pursue. I want to get a little bit more exact answer, or I want to see it visually here. Okay, we're looking at an equation, but since there's a variable involved and the variable is x, we could think about this as a relation between y and x on a graph. So in other words, graph the left side as y equals 3 to the exponent x, and we're also going to graph below that the right side as y equals 7. Now y equals 7, if you forgot the special cases of lines, is just a horizontal line. It's always y equals 7. So picture y equals 7 on the y-axis, cross through that, and always be at that vertical level. That's the line y equals 7. 3 to the x is an exponential relation here, and in this case it's going to have a y-intercept, and it's going to be nonlinear, and we want to know where these two lines cross, because that's what it would mean for 3x to be equal to 7. So we could graph this, and the first thing we probably should do is set our window. So we're going to go in here. Let's assume that the solution is somewhere between -5 and 5. We know the answer is 1.77 as close as we got. So we should be able to find the solution somewhere in there. And knowing that the answer is between 1 and 2, I could probably even go right to that location. But let's just start with the appearance of the graph here. And let's put the y value. Well, 3 to the 5 is actually a fairly large number. So 3 to the 5 is 243. So we need to make the y max fairly large here. Let's go 250. Let's go up by, say, 5 at a time, or maybe even 25 at a time. And I'm going to go back up here. I'm just going to start at 0 actually, because this graph here, look at it, actually crosses through the y-axis very low, and there's my two graphs. Now, of course, the first problem I have is that the solution is very, very close to the bottom of the screen, and I can't really zoom in on that from just looking at it. So I could trace, and I could look at my points, and as I move along, I see the value of 3 to the x, and here I've gone past the 1.77, so my y coordinate is more than 7. That's one simple approach I could do. I could, from that, I could go and look at the table, and the table here is going up by 1 at a time for x, so that's too much of an increase. So I'm going to go and set the table here with second window, and I'm going to have the table start at 1, and I'm going to have it increase by a difference of, say, 0.05. And I'm going to go back to my table of values here, and I'll see when does the y coordinate get close to 7. You'll notice that the second column is the 3 to the x relation, and the third column is always 7, of course. So here I skip right over 7, but I know it's somewhere between 1.75 and 1.8. So I can go back and I can refine my table set to increase by, say, 0.01. That's to do 2 decimal places, and I could start at 1.7 instead. I'll go back to my table here, and now I can see, I'm getting really close to 7, and there I jump over it right somewhere between 1.77 and 1.78. So this is kind of a numerical solution, combined with the graphical solution. If I was to go back to the graph and I just look at that and say, well, that's I got too much information on the graph. I really want to be much closer to the x-axis. So I could just go and change my scale here. Instead of going from -5 to 5, let me go right to, say, 0 as a starting point, and how about 2 as a maximum, and I'm going to increase by, say, 0.1, and then let's go from 0 to, well, I don't need to go any higher than 7, because that's what the solution, that's where the two lines cross, and let's increase by, say, 0.25. So go back here. Keep in mind the scale on the x is between 0 and 2. So now if I was to trace along there, I could find, again, really close to the two lines and the curves where they meet, rather. There's 1.77 at 6.96. If we were to go and zoom in a little bit more, we could get an even better answer. Another option is to use the calculator and to do something which is similar to tracing, but we want to calculate something on the graph. We're going to go second function trace, and here I'm going to put in intersect as an option number 5, and ask me for a couple things. This is, what's the first curve? And you see in the top left hand corner, its equation is 3 to the x, so I say enter. What's the second curve? y2 is equal to the 7, that's the horizontal line, and I press enter, and then it asks me guess where they intersect, and I'm going to go really close with the cursor here, which I move left and right, or up and down if I want, and I can only move along the curves that I'm on. So if I move over to where I think they cross, and then I press enter, and the calculator will give me a value as close as it can come to 2 decimal places, which is 1.77, which is the value I got. So again, here I'm plotting two curves, looking where the two intersect, and I can refine it a little bit with trace. I can look at the second trace option for intersection, or I can go to the table of values, and I can also scroll down to find it there. And then just a reminder, window sets the scale for a graph, second window sets the scale for table of values. Okay, so this was the third strategy. This closes the lesson video. I'll just summarize this last method here. So with technology, when we can't find a common base, the second method is to graph the equations y equals left side, y equals right side on the same screen. Of course, we're trying to find when left side equals right side, so if we plot both of them as relations on an xy axis, the point of intersection will be our solution. That'll be the point where both values are equal, and the x-coordinate of the point of intersection will be our answer to the equation. So in class, we're going to be working again in small groups, looking at a variety of problems to see that we understand the three basic strategies. Independently, you'll have a chance to, again, look at different types of problems, some using common base, some using systematic trial, some using the graphing calculator, and for this one, the feedback problem, I'm going to have you use the iPad again and the graphing calculator to solve number 16, which is a question where you can use a common base, but you can also use other strategies as well. So review the different methods, come in tomorrow, and we'll be ready to work on some questions in a small group. Take care.